So for those of you who missed class today, we are starting on gas laws. And what we did is, to start off, just talked about the difference between a hypothesis, a theory, and a law. I know this is something that we've discussed before, but just wanted to reiterate what those differences are. So we identified a law, since we're going to be talking about the gas laws, as in layman's terms, something that is going to happen over and over again, and we always expect that the same result will occur. Okay, so for example, gravity. We always expect that gravity is going to work. If we drop something in the middle of the air, we expect that it will fall, that it will not just simply float there in the middle of the air, because we've seen this happen over and over and over again. On the other end of the spectrum is the hypothesis, which most people identify as an educated guess. So you may have some sort of observation, some sort of simple facts, but at the end of the day, it really is just kind of a guess. You think you know what might be happening, however, you don't have a whole lot of information to back it up. So that's why you test your hypothesis in order to determine if it is correct. Then in the middle there, we have a theory. And so, based on previous science classes and a lot of other information that you've gotten over the years, as a scientist, a theory is really a lot of facts, a lot of evidence to support an idea that explain why something works the way that it works. So, not only do we have a law of gravity, we have a theory of gravity as well. So, the law of gravity is stating that, yes, if I drop a pen, if I hold a pen in the air and let go, it will fall to the ground. The theory of gravity is going to go into more detail and explain why is it going to fall into the ground or fall to the ground. Um, the way that works is that we're going to have um, this gets into some physics things, but gets into space time and how matter kind of puts a dimple into that space time and affects the way that other objects are attracted to it. And so that's really, an oversimplification of it. But in short, the theory explains why gravity works. The law just says, here's what happens. Okay, and the hypothesis is sort of that beginning step of, all right, I've noticed some things, and so I think that this might be what's occurring. Then you either null that hypothesis, you refute it and say, okay, that's not what was actually happening, or you can support it. So you test it, and then your results of that testing, of that experiment, are going to support that hypothesis, or they're going to nullify it, saying that it does not work the way that I thought it was working. Either one's fine. We just made that analogy to the way that lay people, so just the average person, uses the term theory. And so we just want to keep in mind that as we talk about hypotheses, theories, and laws, that a theory is, from a scientific perspective, is a lot of evidence. We're pretty sure about it. We have a lot of information to support that claim. On the other end, the hypothesis has very little information to support that claim. And so, how the average person uses the term theory is they use theory the same way that scientists use the term hypothesis. So it makes a lot of confusion because people say, oh, that's just a theory. Well, in science, if that's just a theory, we're actually pretty sure about it. Okay, so just a little bit of review on that. Not a big deal. Um, got to this page, and we have the periodic table. The blue elements have they are all gases at room temperature and at 1 atmosphere. All the other elements are either a solid or a liquid. Because we're really living with the gas laws, I didn't highlight the liquids. But just to show that most of the elements are not gases. There are very few elements that do behave as gases. But even if you combine them, there's also a relatively limited number of compounds that are going to be gases at room temperature as well. So we're going to be looking at a lot of these gases and experimenting with them, and most of them will fall into one of these categories. We're going to be dealing a lot with just regular air, which is a mixture of nitrogen, oxygen, carbon dioxide, a number of other items. However, there could be some other gases that get used in some of the demonstrations that we're going to be getting into, which I'll talk about at a later point. So just a quick review from physical science, identifying some of the characteristics of gases. So the first one is that gases assume the volume and shape of their containers. So this is different from solids and liquids. Gases, it doesn't matter what container you put it into, it's going to fill up the entire container. Okay, the gas will fill up the entire container. You've all used water bottles at some point, so you know that when you put water in, it's going to take the shape of the container, but it's only going to fill the volume of how much water you have in there, because water has a pretty standard volume. But the shape is very malleable. I'm sorry, that's probably not the correct word to use. The shape is will change very frequently depending on what container you have. Solids, on the other hand, don't even care. Okay, they're going to do what they want. They have a particular shape, they have a particular volume, and it doesn't matter what container you put it in. So just imagine if you take a rock and you put it in a beaker. Okay, that rock is going to stay its shape. It is not going to change shape to take the shape of the beaker. That rock is not going to expand to fill up the beaker. Okay, so it just is on its own. So gases are unique in that they have their own volume and their own, that they take the volume and the shape of whatever container they happen to be in. All right, gases are the most compressible state of matter. Yesterday we had talked about propane. So most of you have had experience with propane containers. So we can compress gases into smaller and smaller areas so they take up a smaller and smaller volume. And so we can do that by pressing those molecules as close as we can, or keep compressing them more and more. We can actually force that gas, that propane gas, to turn into a liquid, LP, liquid propane. Okay, and so if you've ever picked up a propane tank, you know that you can kind of swish it around and there's a liquid inside. And we started talking about in class today that we can also do this with dry ice. If you've ever worked with dry ice, it's very, very cold. However, all it is, it's carbon dioxide. It's carbon dioxide that has been dropped so cold and compressed to the point that it is a solid. So all those molecules are so close together that they're taking the solid form, and then it sublimes. Okay, and what it means to sublime is to go directly from a solid to a gas, so there's no messy liquid during this process. And so that's really convenient because you don't get your food all wet. A lot of people use it when they're transporting meats because it's both very, very cold and it's easy to clean up. There really isn't anything to clean up. All right, our third physical characteristic of gases is that they're going to mix evenly when you put them in a container. Okay, and so I know I'm a huge nerd, and these are the things that I think about, is I have given the gases certain types of personalities. Okay, so I want you to imagine for a second that we're throwing a party. Right, so we're throwing a party, and we've invited solid, liquid, and gas to the party. So I'm going to just kind of describe what solid, liquid, and gas are doing at the party. So solid comes to the party, and they're just kind of the wallflower. They're just hanging out on the side there. They're not moving around a whole lot. They're not mingling. They're just sort of hanging out on the side and just waiting for everybody else to move around them. They've picked their spot. They're going to stay there. Okay, that's where they're going to stay. And so that is an analogy to the way that the atoms in a solid behave, or the molecules within a solid behave. Because they're just maybe vibrating back and forth, but they're not really moving around a whole lot, which is why they maintain their shape and they maintain their own volume. All right, so solid's pretty boring. They're over there just hanging out and just enjoying the party, kind of by themselves, not moving around. All right, so here comes liquid. Okay, they've shown up to the party, and liquid is behaving the way that I see a lot of high school dances behaving. They're coming out, they're ready to go, they're going to have a good time. But when they actually make it out to the dance floor, they just kind of do a white man over bite, just sort of shift from foot to foot, and not really they're kind of self-conscious. They're not moving around quite as much, but they're still willing to mingle. They're going to go talk to other people at the party. So just kind of the laid back, yeah, I'm going to go around and I'm going to talk to different people, but I'm not really excited, but I'm not, going to be hanging out at the wall either. I'm not just going to stand here by myself. Okay, so we've got solid and liquid kind of nailed down here, but now here comes gas. Okay, so gas is that guy. Okay, gas is the person who is just all over and they're just jumping around, and today is like the best day of their life, YOLO. Okay, I'm sorry that I said that, but they are jumping all over the place and they are just mixed with everybody. They're talking to people, even people who are like, leave me alone. They're going to be all up in their business and they are just trying to hang out with them. Okay, so we have three different behaviors here. The solid is staying pretty tight. They are not moving around a whole lot. Liquid is moving around, but it's not all that serious. Mingling a little bit, but then gas is just all over the place. So that explains why it's taking up the entire volume, also why it's taking the shape of whatever container it happens to be in. Okay, our last one is kind of obvious. Gases have a lower density than liquids and solids, which is why they usually go to the top of a container. If you have a mixture of solids, liquids, and gases, those gases will typically be at the top. All right, so we've talked about the gases and the properties that they have, but now that we have these properties, we need a way to measure the gases. We have easy ways of measuring liquids. We can measure their volume. We have fairly easy ways of measuring solids. We can measure their mass or their volume as well. But gases, we can't do that because their volume is constantly changing and their shape is constantly changing. So we measure gases using pressure. Okay, and so the picture that I have here is of a barometer. Okay, so I don't know if you've heard of barometric pressure, but that is pressure that is measured with a barometer. And if you think back to physical science, pressure is just force divided by area. So these gases are going to have a fairly consistent force, but the area that they take up can change. Okay, so if we take a look over here at our barometer, we have atmospheric pressure. So we know that the atmosphere is full of gas. So that gas is pushing down on this liquid. Okay, and this liquid has traditionally been mercury, although you can use other liquids as well. So it's pushing down on this mercury, and so as the mercury gets, or this liquid gets pushed down, it doesn't have anywhere to go except up this tube. Okay, and so depending on how high the liquid rises in the tube, that is how we're measuring the pressure of an area. So it's a very simple tool. At sea level, we're talking about 76 millimeters of mercury, or in this case, it was measured in 76 centimeters, and that's really just a difference in the size of the diameter of the tube. So we have a very simple way to measure the pressure of a gas. So if we were to take this to the top of a mountain, then obviously the pressure is going to change. So the gas, the air, if I can find my mouse there, the air is not going to be pushing on this fluid. So this level is going to rise because it's not being pushed down by the air as much. And so as this rises, liquid is going to come out of this tube, and so our line is going to drop. So we will have, instead of 76 centimeters, maybe 75 or 74 centimeters of a fluid in that tube. Okay. Now I mentioned this the other day. There are a lot of ways to measure pressure. Okay, so we said that pressure is force divided by area. And so that is pascals. We have 1 Newton, that is our force. We have an area, which is square meters. So that ends up being pascals. Okay, that's all fine and good, except there are other ways to measure pressure as well. For us, we're really going to be focusing on atmospheres. Okay, most of the time we're looking at 1 atmosphere at sea level. It's a very convenient number to use, but you can also use 760 millimeters of mercury or 760 torr, okay, which seems ridiculous because they're the same number. It's just a different label. But using your problem solving skills, if you were to be given a problem that had torr or millimeters of mercury or pascals or even kilopascals, you should be able to take that information and convert it into atmospheres, because that's the main unit that we're going to be working with. So we're going to be working with atmospheres quite a bit. We'll also be working with kilopascals occasionally. But if you are given a different measurement, you can use your problem solving skills that you've learned in algebra and that we've been applying throughout this year in order to convert that. Okay, this is just an example looking at a column of air. So we looked at a column of air that went straight down to the earth. If we start at sea level, then air is going to be fairly thick. Gravity is pulling on the matter. Okay, so we didn't bring up gravity for no reason. The air is made out of atoms. Those atoms are being pulled towards the center of the earth, and so is being packed tighter and tighter the closer you get to the earth. So at sea level, we have 1 atmosphere of pressure. But if we start going away from the earth, gravity is not holding on to those atoms quite as well. So 4 miles up, our pressure has dropped from 1 atmosphere to half an atmosphere. And if we keep going up, and if we go up to 10 miles, let's say, then we're going to drop to 0.2 atmospheres. And so it keeps getting thinner the higher that we go up, because the gravity is not holding on to those atoms quite as tightly. Okay, this is about where we stopped, just looking at the ways to measure pressure. So we can see the pressures in here. As the pressure in here drops, the gas is going to take up less room, so that's going to allow our fluid that is in this tube to drop, okay, to go back up the tube. So it'll go from here, maybe come up a little bit, and so that's going to drop this one, and the distance between the two ends of our fluids are going to decrease. Okay, it's a fairly simple method of measuring pressure. We usually use barometers, not manometers, but that's okay. The big thing that we're going to be focusing on is Boyle's first law, which is talking about as pressure increases, it has an inverse relationship with volume. So volume is going to decrease. Vice versa, if pressure decreases, the volume is going to increase. It's going to spread out because the atoms are not going to be forced together quite as much. Okay? So we can see that inverse relationship here. We can see it's also not linear. So just because you cut it down, and I think you can see that from the column of air that we're looking at, that as when we went from 4 to 10 miles, it didn't change the same amount. So it went from half an atmosphere to 0.2 atmospheres. So it's definitely not a linear relationship. This looks like a linear relationship because we made the volume inverse. So we put it 1 over the volume rather than just volume. Okay, so if we know that as pressure increases, volume decreases, or vice versa, then we can multiply these and we get a constant. But if both gases are going to have a constant, then we can set 2 gases equal to one another. This is where we're going to stop now, because tomorrow we're going to pick up on Boyle's law. We're going to apply that a little bit more and hopefully get into the other 2 laws, the other 2 gas laws, and then you can choose an activity to demonstrate one of these 3 laws. So don't worry about that just yet, but we will get into that next week. Have a wonderful night, and I will see you soon.